So hello, and welcome to our second lecture, dealing with balancing equations. What do you get if you react sulfuric acid with sodium hydrogen carbonate? The products you get from this reaction are sodium sulfate, water, and carbon dioxide. And so that is our reactant in our products. And now we have to go about balancing the equation. And like we said, we have simple rules for balancing the equation. The first rule, of course, is the law of conservation of mass. You have to account for all the atoms on both sides of the equation. Every atom in the reactants has to go somewhere in the products. Every atom in the products has to come from somewhere in the reactants. Second, the law of definite proportions. You can't change the formulas of the compounds as a way of balancing the equation. You have to use the compounds as their formulas are written. And third, we want to start out with the largest species. So we need to pick on somebody complicated to begin with. The sodium hydrogen carbonate looks as complicated as anything. And it wouldn't do us any good to start with the 1 because we already know we need 2 sodiums in the products. So we have to have 2 sodiums to begin with. So we have to start with the 2 in front of the sodium carbonate. That gives us 2 sodiums. That gives us 1 sodium sulfate. And so we have a sulfate in the reactants. Which gives us our next 2 rules for balancing the equation. When you have complex ions on both sides of the equation, you should handle them as pieces and balance them as things. And when you know you're going to need multiples of something, you should go ahead and start with multiples. Don't just automatically start with 1s. So our 2 atoms of sodium gives us 1 sulfate. That has to go in front of the sulfuric acid. The 2 sodium hydrogen carbonates includes 2 carbons. They both have to be going to the carbon dioxide. Which leaves us with the hydrogens. The sulfuric acid has 2 hydrogens. This 2 sodium carbonate has 2 hydrogens. So that's 4 hydrogens. So we're going to need 2 water molecules. Everything has a number in front of it. Which brings us to our next couple of rules. That we have to balance the equation without using any fractions. And at the same time, we want to make sure we're balancing the equation with the lowest whole numbers that work. So after a quick check, we have the lowest whole numbers available. We don't have any fractions. Now we have to count up the atoms. 2 sodiums on the left from the sodium carbonate, 2 sodiums on the right from the sodium sulfate, 1 sulfur on the left from the sulfuric acid, 1 sulfur on the right from the sodium sulfate, 2 carbons from the sodium hydrogen carbonate on the left, 2 carbons from the carbon dioxide on the right. On the left, we have 2 hydrogens from the sulfuric acid and 2 hydrogens from the sodium hydrogen carbonate. That's 4. On the right, we have 2 water molecules for 4. And finally, we have the oxygens. The sulfuric acid has 4 oxygens in it. Each of the sodium hydrogen carbonates has 3. So that's 4 plus 2 times 3 is 10. The sodium sulfate has 4. There's 2 in the 2 water molecules. And the 2 carbon dioxides each have 2 apiece. And that's their 10. And finally, with all the numbers, not fractions, and the lowest numbers available, we come to our last step, where we have to go through and count the individual atoms to make sure that we've accounted for everything in the equation. So what would happen if we combined lead nitrate with potassium iodine? What would happen if we mix those together? And the answer is basically nothing would happen if we simply mix those 2 together. Although those two materials would be more than happy to react if they could, if we just mix them together, nothing will happen. And why not? The reason nothing will happen is because most of those compounds are solids at room temperature. And when you mix solids together, you basically don't get any reaction because the ions can't get to each other. And the solids can't react because they can't actually mix together. You're ending up with a heterogeneous mixture. You just have the different crystals of the material and they're not actually interacting. Which brings us to an important point. If instead you dissolve these two compounds together in water, you get a very bright yellow precipitate out of it. They react quite readily if you dissolve them in water, and this is what we talked about is the important point. It is not enough just to indicate what compounds you are mixing together. You also have to indicate what state or phase those materials are in, because it makes a difference whether they will react slowly, quickly, or not react at all. And so we start having to talk about phases. So we have ways of indicating what phase a given compound is in. If a compound is a solid, then we put a parenthesis immediately after the compound formula and put a lowercase s into it, and that indicates it's a solid. If it's a liquid, we put the parentheses and use a lowercase l. And if it's a gas, we put a parentheses and a lowercase g. And that's if you have pure materials. But frequently, in fact, we work with things that are dissolved in water. And we have a special symbol for things that are dissolved in water. We talk about an aqueous solution. And we put the parentheses and use a small aq after it to indicate that it is an aqueous solution. That is, the materials are dissolved in water. One of the things we want to do is clearly indicate when there's some particular reaction happening. And when you get a precipitate, that means you've formed a solid that was originally in solution. You indicate that often with a down arrow rather than simply indicating it as a solid. In the same way, if you form a gas, you indicate it with an up arrow. And finally, we occasionally give you some extra information, not as either the products or the reactants, but as part of the arrow indicating the progress of the reaction. And one of the things you most commonly see is a small triangle underneath the arrow. This is a Greek letter delta. And the Greek letter delta is often used as an indication of change in something. In this case, it means that the temperature was raised. That is, the material was heated. Occasionally, they'll put some chemical above the arrow as well. And in that case, that material is acting as a catalyst. We'll end up talking about catalysts later. The important thing to know about catalysts is they help the reaction take place at a reasonable rate. But they are neither one of the reactants nor one of the products, so they're not part of the equation when it comes to balancing the reaction, because they're not a product and they're not a reactant. So to go back to our simple reaction between the lead nitrate and the potassium iodide, but this time we're going to have to include the phases. As solids, the lead nitrate and the potassium iodide don't react, but if we dissolve them in solution, as we said, that is, if we make them aqueous, then we do in fact get a reaction between them. The reaction producing lead iodide as a solid, and we could just indicate it as a solid, but like we said, we usually want to emphasize the reaction, and so we give it a down arrow, and the potassiums or nitrates are left in the solution. The lead nitrate's the most complicated looking thing. One of those gives us one lead iodide in the products. Gives us two nitrates. They have to be going to the potassium nitrate, so we need two of those. That requires two potassiums, and that gets us two potassium iodides in the reactants. Everybody's got a number in front of it, we do our last check. 1 lead to 1 lead, 2 nitrates to 2 nitrates, 2 potassiums, 2 potassiums, 2 iodides, 2 iodides. So let's consider another simple reaction. If you take potassium chlorate, add a little manganese 4 oxide to it, stir it together and heat it up, it will in fact decompose. And you end up with potassium chloride as a solid and oxygen gas comes off. And this is the way they used to produce small amounts of pure oxygen when they needed it in the laboratory. They don't do that anymore, but that was a nice old-fashioned way of doing it. So balance the equation. The potassium chlorate looks to be most complicated, so we'd start with that, but it won't do us any good to start with 1, since there's 3 oxygens on the left and there's 2 oxygens on the right. So we're going to need to start out with an even number of oxygens. 2 potassium chlorates decompose, get us 2 potassium chlorides, which are going to be a solid, and produce 3 molecules of oxygen that comes off as a gas. And that concludes our lecture for today on balancing equations. Go have a nice day.